So remember, the ventricles depolarize from the inside out. So when we place leads like this, it means that generally speaking, it's a positive deflection, right? So if we sort of look at the sum total of all this motion, we see there's kind of an electrical direction this way in depolarization. So positive, it's usually pointed, the depolarization vector is usually pointed towards the left side of the patient. We actually call this particular idea the axis of the EKG. In other words, what is the primary electrical vector? More on that in a minute. Okay. All right, so we have we've looked at the EKG. We've talked a little bit about how it's made. Okay, so let's finish putting those pieces together and develop a 12 lead. All right, well, all we've looked at so far is a single lead. And a lead is, remember, it's literally a negative and a positive meter stuck to the patient, right? And we're measuring how electricity moves between those 2 points. 2 points doesn't give us very much information because the heart's a three-dimensional structure. So one lead doesn't help us very much. We need to have multiple leads. We need to look at the heart in more than one direction. So what we do is we use some very elegant designs for electrical measurement that we lovingly refer to as the EKG, right? So if you look here, we have lead 1. Okay, lead 1 is measuring the electrical difference between the two arms, right? Lead 3 is measuring between the arm and leg. Lead 2 between the other arm and the other leg. So by hooking up 3 meters in this way, now we at least are looking at the heart in the circle of the frontal plane, right? So we can then see at different times that the electricity is going in different directions, and we can therefore measure that. Okay, so if we look at our measurements, leads 1, 2, and 3 here, we can see, first, notice the commonalities. While the QRS complexes look different in each lead, they are all happening at the same time, right? The P wave and T wave look different in each lead, but they're all happening at the same time. Why? It's the same event. They're measuring the same event, which is that contraction. Okay, they're just, you're measuring it from different angles. You're looking at it from different points of view. Now, we do some fancy electrical analysis in the way that we can sort of sum these. And I think the physics here isn't as important as what you get out of it, which is 3 leads with 3 views of the same thing. Now, this lead, like lead 2, is looking at the heart this direction. Lead 3 is looking at the heart this way, and lead 1 is looking at it this way. See, so you have different angles of the same thing. Because of this, lead placement really matters. All right, if you don't place the leads correctly on the patient, what the EKG you get won't be an EKG. It will be some other measurement of electrical activity, which is not an EKG in any way. So you do have to know exactly how to do that. We're going to teach you how to do that, how to put leads on a patient so that you can accurately get an EKG. All right, so that's leads 1, 2, and 3. Back here. Too far. Yeah. So that's leads 1, 2, and 3. Now we take our very elegant electrical setup, which is a nice circle called the Cabrera circle, and now we make it more complicated with additional views. Okay, so we have the these are the limb leads 1, 2, and 3. Now we're going to add the precordial leads. So remember I said before we had the frontal plane circle. The precordial leads give us the coronal plane circle. Okay, so looking around the heart. So V1 is over here. It's actually to the right of the sternum. And then we get 2, 3, 4, 5, and 6 that go around. And then there's additional leads that continue to go around. So we call these the precordial leads because they're in the front. So V1 and V2 are both to the right of midline. V3 is sort of in the middle, right near the heart's apex. And then V4 is typically most aligned with depolarization. In other words, it has the highest QRS. Lead V3 usually has the most balanced QRS complex. V1 is usually very downgoing, right? Because of V1's way over here, and the electrical vector is where my arrow is. See? So if the electricity is moving away from V1, then we get a negative deflection. So it does match what we know. So each of the precordial leads is very close to the heart. So we see the amplitude of the waves are generally higher. This can be useful because as we're assessing the EKG and we're trying to find heart damage, okay, the precordial leads, because they're so close to the heart, they show that damage very well. You know, so like in our ST elevation MI, for example, you'll see changes in some of the precordial leads, and it will give you a clue as to where the problem is, where the myocardial infarction, where on the heart it is. Okay, so limb leads, precordial leads, last electrical trickery, augmented limb leads. And here, with the use of complex resistors, and if you are engineering minded, 5,000 ohms is a lot of ohms, just saying. Like, so that is a significant amount of resistance. But what it allows us to do is we get sort of 3 more views with our augmented leads, AVR, AVF, and AVL. So AVR is from the right arm's point of view, AVL is from the left arm's point of view, AVF is from the left arm's point of view. All right, so all of these, because they're so distant from the heart, we get a good view of the whole heart, not part of the heart, like we do with the precordial leads, right? So these are further away, but by the time they get there, we see the big system. Okay, so when we look at all of these leads are going to appear on the same piece of paper at the same time. All right, so what you'll see is this is our piece of paper, and it'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 leads, right? The squiggles in each section will be from the particular lead that we're looking at. All right, do I have a full-on EKG in here? Yes, okay. So this is an EKG minus the rhythm strip at the bottom. Okay, so we see 1, 2, 3, AVR, AVL, AVF, V1, 2, 3, 4, 5, 6. All right, so we're seeing 12 leads, the view from 12 leads. Now, one of the places that I think students get confused is this complex, this one, and this one are all happening at the same time. Okay, so what you have is you're looking at the same events from multiple points of view. Okay, and we'll put the pieces together here in a little bit. Okay, so augmented limb leads and then the Cabrera circle. So if we simplify our view of the EKG with all of our leads, not all of our leads, with our limb leads, so 1, 2, and 3, AVR, AVL, and AVF. So these leads and these leads, okay? So our 6 limb leads, augmented and regular, we can construct what's called the Cabrera circle. This is in the coronal plane. No, this is in the frontal plane. Okay, the Cabrera circle is in the frontal plane. If you can imagine the heart sort of sitting in the middle of the circle, right? And typical depolarization is this direction, right? Because the heart sort of points to the left and down. So when the heart depolarizes and repolarizes, the direction of that vector is called the axis. Okay, so imagine this. Imagine you had the left side of your heart was severely damaged. In other words, it had many fewer cells than it typically would. Well, instead of the axis pointing towards the left, it would drift towards the right because you have more muscle cells on the right than you do on the left. So the axis of depolarization tells us how balanced, how healthy, for lack of a better term, the heart is. Okay, so the way this circle works, each end of the star is a lead. All right, so this is +1, this is -1, right? Lead 1 positive, lead 1 negative. So the up arrow is positive, the down arrow is negative. Here's AVR, right? Negative and positive. Lead 2, positive, negative. AVF, positive, negative. Lead 3, positive, negative. And then AVL, positive, negative. Don't worry about why is it positive and negative where it is, because that's how it is, right? Because the next step is a lot of electrical physics that I've always struggled with. So that is the way it is, right? Okay, so what does that mean exactly? Well, it means that if we have a lot of activity going towards lead number 1, and we don't have much activity in the other regions, then that means we have an axis of 0, right? So uncommon, but I think it makes the point. The problem with axis, it gets very complicated, right? And you're not ready for complicated.